Welcome one and all for the webinar from ASET, Amity University, Haryana. As you are aware, AUH is known as Research and Innovation Driven University. The birthday of Honorable Chancellor Dr. Asim Chauhan on 28 September 2020 is celebrated in the campus as Innovation Day. Every year, 1 week prior to the celebration of Innovation Day, many activities of research and innovation were conducted and displayed. This year also, amidst the pandemic of COVID-19, AUH is organizing webinars from renowned resource persons and carrying out the research and innovation activities. The present webinar is one of the series being conducted by Amity School of Engineering and Technology under the banner of Amity University, Haryana. We thank the Honorable Chancellor, Vice Chancellor and Pro-Vice Chancellor for their motivation, support and guidance for carrying out these activities. I wholeheartedly welcome today's speaker, Professor Ajay K. Mishra from University of South Africa for this event. Rashi, for you now.
Thank you, sir, for giving the opening remarks on the eve of the celebration of Innovation Week 2020. So I would like to introduce Dr. Ajay Kumar Mishra to one and all. Ajay Kumar Mishra is a professor at the Institute of Nanotechnology and Water Sustainability at College of Science, Engineering and Technology, University of South Africa, Florida. Professor Mishra recently has been recognized as fellow member and also chartered scientist at Royal Society of Chemistry, UK. He received his BSc, MSc degrees in 1997 and 2001 respectively from Purvanchal University, Jaunpur, India, and MPhil and PhD degrees in 2003 and 2007 respectively from the University of Delhi, India. Professor A.K. Mishra research interest involves in the broader areas of nanoscience, nanotechnology, material science, polymers, composite nanocomposites, and water research. Professor Mishra successfully developed smart bio-nanocomposites for organic dye remediation in his water research commission project, which involved a visible light-driven photocatalyst based on the rare earth metal, and the same has been tested in the various textile industries within South Africa. He has authored over 150 scientific papers in peer-reviewed international journals, 61 book chapters, and 29 edited books. Professor Mishra has supervised and graduated 9 PhDs, 20 masters, and 12 postdoctoral fellows, and 15 PhDs, 2 masters, and 1 postdoc are already working under his supervision. He has more than 83 plenary keynote invited lectures and has also attended more than 150 international national conference workshop and symposium. He is serving as a member advisory board of a number of international scientific societies, conferences, and workshops. Now I would like to request Dr. Ajay Kumar Mishra to kindly please proceed with the guest lecture on the applications of organic and inorganic hybrid materials. Over to you, sir.
Welcome, sir.
Oh, thank you so much, Rasi, for nice introduction. And then I also thank Dr. Sridhar for opening remark. I think Ajay expressed like this is my pleasure to meet with you today, and this is my second meeting we are doing, and I think like as going forward we are going to have a nice interaction today. Dr. Sanjeev Sharma, I wish to also thank you in terms of like, always remember in terms of even welcoming and sharing. So today I'm going to talk something a bit different, in terms of like how we are making some organic and inorganic hybrid material, and how this is going to be applicable in terms of the wastewater research. So I think Rasi, again I want to thank you, because usually nobody reads the whole biography, but you have read all of them. Okay, and that sometimes feel like you are getting too old. All right, so with that note, let me just start my presentation. I have to just check like whether all the participant and everybody can see my slides. The full picture. I just want to.
Yes, sir. Yes, it is visible. So it's in the full slideshow mode, sir.
Right. I don't know whether anybody can control the video so that it can be off, because my screen is just flat now at this moment. Do you have a control, Rasi?
Yes, sir.
Yeah, so can you switch off most of the video so that it can go very nicely? Okay, so today I'm
Sure,
going
sir.
to talk, I'm talking about the application of organic and organic hybrid material. Um, Obviously, like if you try to see, like I come from South Africa, which is the southern part of the Africa, and in terms of the population, we are close to 59 million at this moment. And even with the COVID, we have done quite well, because now we are moving quite good way in terms of like improvement. So we were in the lockdown 5, which was like the extreme one, but now we are in lockdown 1. Even the death rate and other things is quite improved. So I think we did quite well in that sense. And obviously, like I wish actually like our own native country, India, can also do, because I see the statics is also coming down. But nevertheless, let me just try to tell, like I am, staying in Johannesburg itself. So just to give you a little bit more idea about South Africa, like we are 59 million people, and we have around close to 9 provinces, 11 official languages. The racial, demarcation, if you have to see, like it's around 80% population is black. It's close to 8 to 9% is white, and close to 8 to 9% you can say it's Asian, which means like Indian, Chinese, Pakistani, Bangladeshi, everybody you can try to count there. Um, so out of 9 provinces, like I am based in Johannesburg, which is Gauteng province, and there is two big city you might be knowing, which is Pretoria and Johannesburg. If I have to elaborate a little bit on the Johannesburg itself, like Johannes means gold and Berg means mine. So it's gold mine. So every 100 meter, if you have to walk around, you can see. And you can see the live picture of Johannesburg in the night. How does it look like? And then the campus, the main campus, you can see for this is the main campus looking like, but we have around close to 77 campuses in total. But that is not within only in South Africa, but also other side. So as I explained, actually, like you can see this is a place of gold, platinum mines you can see, and then city is also known as like nickname Joji or City of Lights. That's how it goes. But the whole idea comes like how we can be very responsive in terms of nanotechnology, because I'll go through a little bit more details in terms of like how the nanotechnology was coming together in the beginning. But if we have to see right here in terms of responsible nanotechnology, I have to play this. I think most of you have seen this movie called Spider-Man, but many of you may not be aware like this spider feet is made up of nanoscale fiber. So those things should also comes to our daily routine in terms of research, actually, like although we are looking for the use of nanotechnology, but how we can be responsive in terms of the toxicity. So with the phrase, it goes itself like with the great power comes great responsibility. So obviously, like our responsibility lies more in terms of like how safer way we can try to use. But if you have to talk about this nanoscience and nanotechnology, and if you go to the Google search, it's more than 1 million hits immediately comes, and there is a lot of bigger terminology is also coming there. I'm not going to go those kind of more details, but what we are looking actually like on the government and the industry, like how the millions of dollar in the nanotechnology is getting invested, and those things is how going to be more beneficial. So is this the next IT which we are looking as a huge salary? Obviously, that is a matter of thought. One can think, or can it stop aging and cure cancer, or can it get me safe water? is nanotechnology factual or a figment of imagination? So obviously, like these kind of questions, we need to think, and some of the solutions lies within. We have certain solution if we have to talk about, like, can I get me safe water? Obviously, if you see your own house, you have the RO system. That is one of the, the discovery coming from the nanotechnological help, the filters and the membranes, how people are trying to use. But again, as I told, like how we are going to go towards the responsive nanotechnology, that goes like, is this nanotechnology is risky? So that is a bigger question. So we need to separate what is fact fiction are between hype and hope. So those kind of questions I bring to all the researchers, how we are going to go towards this nanoscience, nanotechnology. But in terms of like coming for the water disinfection, if you have to see, there is a variety of metals. If you see like the silver, copper, zinc, titanium, cobalt. So there is a newer type of dynamic materials is being exposed. And then what they are trying to do actually, they are having different kind of groups. They too try to interact with each other, and that's how like in terms of the water disinfection, it goes there. So I'm not going to go more details, but I just wanted to little bit highlight on that side so that you are a little bit aware what I'm trying to talk about. But let us talk about today certain things. But before I go to the hybrid material, like a kind of composite material, which is a material of 21st century. So in nutshell, what is the composite material, which is just nothing, is just like composed of two or more different constituents. And if we have to separate in different segments, what you can say, like it's a hybrid material, metal alloy, a nanocomposite or macro composites. And you can easily see from the diameter how you can play around in terms of making the hybrid material or nanocomposite material or the macro composite material. So the whole idea is like, if we try to engineer the material, that's how the whole application or the properties used to change. So why we are looking this? Why we are looking this kind of composite material or hybrid material? So we are looking, the goal is to create material with specific combination of properties by combining different molecular building blocks in various ratios and by controlling their mutual arrangement. Why? Because we are controlling at the nano level, and if we can control, we can have a larger surface area, and then we can try to see the application what we are looking. And I'll be a little bit more focused into like how we are going towards the wastewater treatment later on and the scale. But if you have to see between the composite material and the hybrid material, and if you have to go like how you can compound, and that's how you can control between the macroscopic phase and the nanoscale building blocks. And those things are quite important in terms of like how you have to control at the nano level. So with that note, let me just bring to your attention today that whether it was existing in nature, obviously it is. And these are the, this slide especially like quite, important just to see for you, like, Ernst Haeckel. I don't know, many of you are known, but there is a paper published in Nature itself in 1904, where they were trying to, bring this kind of, the structure, what is coming like as a natural form of this organic and organic hybrid materials. And then if we have to go for the more application point of view, then you can see like this is going towards like a packaging material. Obviously, you have to tailor the property, which is like a gas permeability. It goes via the polymer and silica itself. And I think there is a lot of processes involved. So as we go, we can try to see like what else we are covering today, but just a little bit example how we are trying to go. If we have to make some optical materials nowadays, if you have to go to like little bit more expensive hotels, you can try to see, and even the cars, you can see like this kind of optically sensible glasses is available. And then we are having like the optical polymers with extraordinary mechanical properties. Obviously, we are engineering between the nanoparticle itself, whether it is a silica, titania, alumina, zirconia. That's how researchers across the world they are trying to make it. But in terms of like polymers for decorative application, nowadays you can see like most of the good houses, people are putting this kind of hybrid material as a decorative pieces in their houses, and obviously like it is not very dangerous or toxic, so and it looks quite pretty. Then obviously like electrical conductive polymers. So we have a variety of example as we can try to see. Now, the idea is like if we are looking behind this application, then as I told in the beginning, like this is the material for the 21st century. What we have to see, we are looking on this salient feature, which is the characteristics of the both constituents. This is like existing naturally, which is nails, hairs, horns, skins. Obviously, like it is a tailor-made material. And then again, we have to play around the size. So that's how we can see the features. If we have in our mind, then we can try to see actually like how we are going to go more further. So if we have to talk about this composite material, which is a kind of hybrid material we are talking about, then we are going to have some precursor, and then these precursor is going to be in the form of molecular precursor clusters, which is like nano building blocks. Then alkyl substituted organic polymers. I think I'll go a little bit more details on that. Then pre-formed nanostructure. So those are the precursor materials we are also working. Then if we have to talk about the classes of sol gel hybrid material, that is like why we are looking more there. So this is like a physically interwrapped component, functionalized inorganic network, interpenetrating network, and dual network. So that is why like we are more looking there. But in terms of like the challenges, that issue in terms of the preparation, if we have to look there, we need to also find out actually like certain things, what should be our objective. So whether it is homogeneous, so that is the one question we should have. Is it going to be a stable distribution in terms of like how we are going to go in terms of the phase separation? Then the interaction in the two components, how they are strongly interacted with each other. Then we have to see about the structure property relation. That is very, very important factors right here. Then we have to go around and see inclusion of functionalities. Obviously, like how we have to do the tailoring of molecular structure to nanostructure to microstructure, and that is like being resonant. So the whole idea is like why we are looking this kind of tailoring, because we are RTL this structure design, and obviously like all these properties is quite important in terms of what kind of application we are looking. So if you have to see the approach to prepare organic inorganic hybrid material, you can easily see like this is one side is like a precursor chemistry, and other side if you see the building block up approach. So in terms of the precursor chemistry, if you have to see, then there is a chemical interaction change, properties of the precursor, then properties of final materials are different to the precursor, and then how we are trying to make it in terms of like the sol gel, the organic polymers. I'll go a little bit more details like what I'm talking, but Little bit on the introductory note, I thought like, let me just share with you. So in terms of the building block approach, if you have to see, then this is looking on their molecular integrities, at least the partial one, and then properties of final material to keep similarities to the precursor. And then the typical material, if you are looking like the cluster and particle cross-link material, and you can see easily about the polymer cyclodextrines, to name a few, as we move or we are working in that direction. So then the question comes like, what are the techniques to prepare this kind of organic and organic hybrid material? There is a lot processes is there, but the most popular one, what I try to highlight today is like the polymerization and polycondensation process. And then there is a very well-known salt gel process or the self-organization process. So these are the three main, processes which is involved in terms of like the preparation of organic, inorganic hybrid material. But in terms of like the salt gel process, if we have to name one, like how we are going to go, and prepare. So obviously, like we go with the hydrolysis and the condensation, and if you see there is a metal alkoxide, and if we hydrolyze, that's how you can get your the resultant material. And then we go further to do the condensation process, where it goes the cross links, and that's how you go. And then in terms of like the moiety, if you have to say, there is some research moiety, and then there's some metal moiety, so you have to change, actually depends what kind of resulting material you are trying to prepare. So in terms of like, if we see this hydrolysis and condensation process, it goes via two ways, whether it is going to be acid catalyzed or the base catalyzed. So we try to use both ways, where we are using the acid. Sometimes we are trying to use as a smaller quantity, like with the hydrochloric acid, we try to do. And then the base, like we are trying to use the methanols and others, based on with the precursor material. So obviously, if you have to say with the acid catalyzed, what is happening is there like yield primarily linear or randomly branched polymers. So what you are looking, those kind of things you need to see, actually whether you have to go with the acid catalysis process or the base catalyzed process, which is like yield highly branched clusters. So those things is quite important to all of us in terms of understanding, like what kind of materials we are trying to make it. Then in terms of like, if you have to go for more understanding, because we know now like what is hydrolysis, what is condensation, and then what are the acid catalysis process, what are the base catalyte process, then it comes right there, like in how the whole process is happening in terms of the final product using the salt gel process. So we have the salt processes, the salt, it via with the esterification, you can say like we are making some gel, and those gel, it can go to the supercritical extraction or the solvent evaporation. Then it goes to the zero gel or aerogel, and after drying you can get the dense glass. Obviously, if you are going to the salt processes, you have the salt fibers. Then with the salt you can get the powder. I'll tell a little bit more details as we go with our research, like how we are trying to make it there. Then with the salt, you can go with the zero gel film. Then via the heat treatment process, you can get the dense ceramic film. And you can easily see from this slide, like in terms of preparation, this is quite important, because all these things is going to directly affect in terms of the whole properties of the resulting material, and obviously that affects directly to the application of the material. So now, if we have to talk about the polymer blending technique for the combination of sol gel derived inorganic nanomaterial with organic polymer to prepare organic inorganic hybrid, it is quite important to understand actually, like when we talk about the organic and inorganic, and that's how the sandwich compound is going to be the hybrid material. So why we are looking that one, that is quite important. So I'll go a little bit more details on that, like how we are going to look or why we are making that way. But in terms of the understanding, you can see like if there is a polymer and there is some silicate layer, and that's how you can try to form. And these are the work what I am trying to say is like already published, and you can easily access in terms of the in the market, the research domain as well. Okay, so if we have to see many other examples, we can try to find it out, like what are the polymer blend techniques, or how this sol gel process works in terms of making different or new kind of hybrid materials, right? So why I was taking all these stories together, because I just wanted to tell you like what we are making using this organic and organic hybrid material to make silicon carbide. So that was the whole objective behind today's talk, and that's what I was trying to introduce the whole scenario and the processes involved, so that you will be more aware. If you like, there is a lot of things, but why we are more focused on that side. So obviously, like if we have to talk about the silicon carbide, then the discovery happened in 1893 by Dr. F.H. Moisan, naturally found first. It's Kenyan diabolo metallic Arizona, USA. So that's how it is there. And if you have to say natural occurrence, then there is a moissanite, rare earth minerals, meteorite, then corundum deposit, and kimberlite. So these are the way it goes. And obviously, if you have to see some of the structure right there, you can see the silicon carbide is also known as a carbo random, and it is compound of silicon and carbon. The chemical formula is SiC, and it occurs in nature as the extremely rare mineral moissanite. So this is quite important to understand before we go, like why we are making. And obviously, like this is existing in around 250 crystalline form, and the polymorphism of silicon carbide is characterized by large family of similar crystalline structure called polytypes. So there is a variety of polytypes of silicon carbide is available, but we try to focus actually in two of them, but one is more dominant one, which is, so we'll go a little bit more on that. So why we are looking on this silicon carbide polytypes, and then if you have to go on the salient features, you can see the silicon carbide occurs in different crystal structure called polytype. And the polytype is nothing is different stacking sequence of silicon carbide bilayers. All silicon carbide polytypes chemically consist of 50% of carbon atoms covalently bonded with 50% of silicon atoms. And the common polytypes, you can see 3CSIC, 4HSIC, 6HSIC, and then obviously like it is the electrical device properties are non-isotropic with respect of crystal orientation, lattice side, and surface polarity. So those are the things which is very important. But in terms of like the polymorphism, what I just now say for understanding, you can see like this is a similar crystalline structure, identical in 2 dimensions, but differ in third form. So this layer of silicon carbide is stacked in unique sequence. Number of polytypes, as I told you, like it's around 250. And the common occurrences of polymorphs is alpha silicon carbide or beta silicon carbide. Obviously, like in terms of the alpha silicon carbide, you can see it's like if you have the temperature around greater than 1700, it's around like hexagonal crystal structure. Then if you have to talk about the beta silicon carbide, which is less than 1700 temperature, and then it is like a zinc planed or cubic structure. So these are two is most abundant polymorphs which is commonly occurring, and we are more focused on the beta silicon carbide in terms of preparation. So why we are making the silicon carbide, if you have to see there. So then if you have to see the commercial application, and those commercial application is coming towards like resistance to abrasion, heat and oxidation. Obviously we are from we are interacting today, and you are from mechanical engineering, so you can try to understand more deeper way that side. And then obviously, like if you have to look about the wide energy gap, it is the range of around microwave. So that is also quite important, And then if you have to see like the high temperature resistance, that's how it is. It is highly applied. Then rigidity, lightweight, corrosion resistance, and obviously like nowadays people are looking on the biocompatibility. So I'll go a little bit more details on that, if you like, what are our approach in terms of putting like how we are making, and uh, uh, what are the way forward we are looking this kind of materials. So in terms of preparation, what we are trying to do, actually, like we are taking some precursor material of silica sol, and I think no need to go more details because I have already spoken in the beginning, actually, like what are the precursor, and what are the types, how does it work out, why we are looking that one, how they can make building blocks, so there is a lot of things I have already spoken. But here, the two kind of precursor we are looking for the silica, which is MTES or TUS. So MTES is methyl triethoxysilane, and TUS is tetraethoxysilane. So these are the two most abundant precursor of silica we are trying to make, and the whole objective, like we are trying to make a polysilane. So the reason behind making polysilane, because we are looking the inorganic component in terms of the nanoparticle in terms of the sol form, and those sol form, if I have to go back a little bit here, you can try to see, like those sol form, it can go right here in terms of the powder. Sometimes you have to do the calcination. I have not covered today's in that talk, actually, like how we are calcining and where we are trying to use it in that way. Then obviously, like you can make a film, or you in the same sol form, you can try to make it your hybrid material, and that's how you can go more further. So that is way actually we are trying to make using these two precursor material and making some polysilane. And obviously, like if you have to understand the more deeper on the methodology, like how we are making this inorganic hybrid material, then you can see like the first source we are taking is like polymer, and the polysilane. Now you have the understanding right here, like these are the polysilane we have prepared using this the precursor. Obviously, like this precursor goes via these two processes called hydrolysis and polycondensation. So once we have the polymer and the polysilane, which is a form of inorganic hybrid material, then we have to go for the carbothermal reduction. And those carbothermal reduction, which is a terminology called pyrolysis, it is between 1200 to 1400, and this is based on the literature as well, and we have also synthesized, and so we have prepared that material, and we have already published. So if you have more interested, you can try to see more details on those papers, and then you can further interact. So obviously, like with this carbothermal reduction, the pyrolysis process, what we are trying to do, like you can see from here, like the polymer is coming in the form of carbon right here, and which is a organic material, and then this is polysilane is coming in the form of silica. So these two things is like inorganic and then the organic, and that's how we are making this silicon carbide using this carbothermal reduction, which is called as a pyrolysis. Then obviously you need a furnace for that, and you need to also have the inert atmosphere for that one. So those are the processes we try to bring it together. So obviously there if when we try to generate the silicon carbide, then the amorphous carbon and the unreacted silica also goes together. So how to remove those amorphous carbon or unreacted silica? Obviously, we have to go the oxidation process. So within the furnace, we do the oxidation process from 700 to 800 degree centigrade. And that's how we get the silicon carbide. And obviously, it is also combination of the unreacted silica, because we get rid of the amorphous carbon, but still the unreacted silica is right here. And then if we have to get rid of unreacted silica, what we have to do, obviously we have to do the HF treatment, which is quite a dangerous process in terms of like you have to have the platinum type of crucible, which is also one of the costs we need to look there. So obviously we have those kind of facilities. So and even for the HF treatment, we have the process in place, how we try to engage this study. But here the whole issue, what we are conducting the research, the whole issue comes right to us actually, like it's very poor yield, and the impurity is also a bigger problem. So that is the thing we are trying to look, because after generating this one, and I will to tell you the source as well, like how we are trying to generate different kind of silicon carbide material using different kind of the source of carbon, which is quite enthusiastic in terms of carry out the research in the past as well as in the future. But obviously, like we are working more on like how we can go more yield of the material, or how we can remove the impurity of the material. So one of the sources actually like coming right here, I'm so happy that we are talking, to Amity University, because the first project actually like it was done in India when I think it's around close to 20 years, from now you can see. So we had a project from Ministry of Environment and Forest where we wanted to remove the polycyclic aromatic hydrocarbon from coal tar pitch. And obviously, like we were using those two standard techniques, which is the solvent extraction or the thermal. So the whole idea is like once we have the heat treated one, or we have done the solvent extraction process, then the material is almost like useless. After that, what we are going to do? So then we try to do the carbonization process, and that's how we try to understand actually like how much carbon is there and whether it can be formed. So after that removal of polycyclic aromatic hydrocarbon, and namely it was benzoapyrene what we were dealing there. So obviously, like when we removed it, so we go to this kind of process of Sol-Gel process to make the polysilane, and then we have this the carbon source coming from the coal tar pitch, and that's how we make this silicon carbide. So obviously you can say that is the waste material, which is like in the form of the processes it happen, but later on actually like we try to make use. But again, the problem what we discovered, what I have just shown you from the last slide actually like that is the poor yield, and in terms of the impurity was also a bigger issue. So that is a very good way of seeing. But if you see the second picture, which is this one here, if you go to the previous slide, like we talk about the source of carbon is the polymer. And here we took the polycarbonate, and you can easily see the pictures. It's quite nice, quite amazing. Even the uniformity you can always try to see that way. So that was also quite good, and it took also very less time in terms of the production or the publication. But nevertheless, what I wanted to say more on your side, actually, like the third aspect what we try to cover. The third aspect what we try to cover, actually, like we try to take the source of carbon from the waste. And I think most of you are aware, actually, like, you are writing nowadays very nicely on the paper, and you are quite good there. But just to make the paper process, if you go to the industry, you will be quite amazed to see, actually, like how they are making. But obviously, like with the pulp and paper mill industry, they try to have a lot of lignin right there, and obviously, like coming from the black liquor. So the whole idea is like from the lignin there is a lot of carbon present right side there. Obviously, there can be sorry, more challenges on that. But what we did, actually, like we took we went to the pulp and paper mill industry, and we extracted the lignin out of there. And obviously, like we took the source of the inorganic material, which is the polysilane, in terms of the precursor what I mentioned, both MTUS and TUS. And then we have done the carbothermal reduction. I can little bit go back to just to show you, like this is the whole processes. So in terms of the polymer, here is the source is coming from the lignin, which is coming from the pulp and paper in mill industry. And then the polysilane is coming in terms of like these two material what I talk about, like whether it is MTUS or TUS. And that's how we make together, and finally we get this compound called silicon carbide. So that's how we did. But again, if you see the whole picture right there, you can see with those processes, it is like a little bit lumpy. If you see there, and there was a lot of nodes we had discovered. So we were trying to find out like whether they can be joint, so that we can combine the making some like linking those things together. But obviously, like the size was quite interesting in terms of the length of the fiber. You can also see from this the TEM transmission electron microscope photograph. And then the second one is like with the craft lignin. So we buy from the market, which was, and you can see, but there is both pictures are quite different. This is from the straight away from the pulp and paper industry, and this is from the craft lignin. And these are just HRSM images that we have tried to put it there. And obviously, like this research has been also published. So if you want to have more details, we can see there. And if you see like this whole bunches, if we have to go more details on that, and then that's how we try to conduct this the HR TEM, which is high resolution transmission electron microscope. And this is only for the paralyzed sample, like I wanted to say today with you. And you can see like this is looking like a bamboos. So the moment we try to discover this one, and the guy who was doing the TEM, he was quite happy. And I think I remember like quite a few months he just put it there. He's very well-known researcher, but he put it in his screensaver, so that he can show to the people like from the waste what you can generate, and it is quite nice. So what was happening right there, like what I was trying to share with you, like how you can generate some junctions. And that is, you can see we try to generate the Y junction, which is like in terms of joint we have done. And those like if you have to say the crystal structure, how it is looking around. So that was, and then we also concluded like it is going in the form of like beta silicon carbide. Obviously, like there is different terminologies, there are the techniques you can try to confirm with that way. So, and you can see, like, if you have to go like a more internal morphology analysis, and then you can easily see actually like like how the crystallographic data is looking like in this one. And the important thing behind this, if you try to recall, and I go a little bit more further to understand like what is here. If you see this picture right here, and it is looking like bamboos, and then what is on the sides. So those things is quite important, because if we have to carry on more further, we need to know, because we are looking more application, more yield, and the purity of the compound. So obviously, like when we did the study, we did try to find out like these are nothing, those the outside border is nothing. It's just like it's a silica, and then the inside is the silicon carbide. So then what we have done actually, like that's how we conducted the HF treatment, and that's how we get the pure silicon carbide. Okay, and you can easily see from this graphics very well. So then the question comes again together, like how like this is a beta or the alpha. So obviously, like we have to conduct the Raman and the FTIR, and you can see like the peak at 805, and that is also supported by the literature that this is a beta silicon carbide. And obviously 475, it is showing silicon O, oxygen silicon, unreacted silica. And then if you have to talk about the 1100, that is OSIO, unreacted silica. So those are the quite important things what I wanted to say. But what is linking to this kind of organic and organic hybrid material what we have prepared, it's quite important, because if you have this material right there, which is the together with the silicon carbide and the silica, right there, then obviously like you can functionalize, and you can attach with the DNA. So that is one of the application we are looking. The metal complexes, it can be formed actually, so that can be another way of looking, the application. Obviously, you can immobilize the enzymes and the quantum dots. So these are the four we thought about, but now we are moving more further, like with the Fischer-Tropsch, way, and that is some ongoing project where we are trying to make use of this silicon carbide as a catalyst material. And then obviously, like it can go for the synthesis of some ethanol or methanol production, but that is a different group trying to do. But the whole idea behind us, like from the waste we can try to make this silicon carbide, and after that it can be functionalized as a better catalyst, and that's how it can go more further. So I have to little bit go on concluding side now. So I have to tell you, like these are only few books I have highlighted today, like which is having more on the sol gel way. If you are looking like the sol gel nanoceramic material, or the carbon based material, or they are looking for the inorganic oxide material, so, and the smart ceramic, so those kind of this is also in the Google. So I have around more than I think you have highlighted there, but these are the one actually I only highlighted so for this lecture, so that if you are interested, you can have more studies there, and that will help. So I wish to acknowledge my team, which is all over the world actually, and I wish like peoples will be also from your university coming together, working together, and that's how I believe. Because my belief is an open mind and nurture scientific thinking, and that's how we can go. So these are the team members, and this is a very perfect example of organic and organic live material. These are my two daughters. My wife comes from the organic background, and I am from the inorganic background, and these are the two hybrid live material I can show with you. So my teams are also there, my partner from Russia, from Canada, from the UK. So all are coming right there. And that's how I want to conclude, saying that knowledge has only beginning and no end. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Thank you, sir, for sharing your work, your experience in the field of the research and knowledge with us. I can assure you that we have gotten benefited by this, talking about materials of the 21st century, their characteristics, and applying them and showing the pictures at such a basic micro level. It's really quite beneficial. Thank you, sir, once again. And now I would like to request Mr. Om Prakash, sir, Faculty Mechanical Engineering Department, to kindly ask questions on behalf of the attendees, participants, if any, sir. Over to you, Om Prakash, sir.
Om Prakash, unmute yourself.
Now am I audible, sir?
Yeah, we can hear you.
Yes. Thank you very much, sir,
Yes,
for a
yes.
wonderful talk on application of organic-inorganic hybrid materials. Now we have some questions from our participants.
Go ahead.
So the question is, as there are different polytypes of silicon carbide like 2H, 4H, 6H, etc., which is best for refractory grade and why?
To be very honest, like what we are trying to make use of this the waste source in terms of carbon. So what we are making actually like the use of this whether it is coming from the Croft lignin, whether it is coming from the coulter pitch. So obviously like that depends actually availability of how much carbon is present right there. And once it is there, then we need to also establish in terms of like whether it can be, so those kind of things we need to see actually what are the applications one is, looking for. Then we can try to explore and, reveal that way.
Okay, sir. Next question is, sir, what are the application of silicon carbide in medical science?
You see, there is a lot nowadays, because if you just Google it, I no need to name all of them. So if you have to talk about the dental brasses or, so there is a lot of, application is coming, but we are not more focused on that side. But obviously that is one of the application you are, you are looking.
Okay, sir. Sir, next question is how silicon and carbon bilayer are getting stabilized in carbon structure?
I think I did try to see when I was trying to tell about the history itself, how the silicon carbide, what are the structure, how it is formed actually. So it is quite, interactive. And then once you do this pyrolysis process at around 1400, around 1200 to 1400, that is the literature itself shows. That's how you make that silicon carbide. And obviously like for that confirmation you need to do, and the simple way to confirm is like the FTIR. And I think during my last 2-3 slide I did try to say like this is the way you confirm whether it is a beta form, whether it is alpha form, and that's how you can try to confirm. And later on, like when you have to do like with the morphological structure, especially with the SEM, which is scanning electron or the transmission electron microscope, and that's how you can further confirm.
Okay, sir. Next question is, sir, what is the impact of nanomaterial on sustainability in terms of environment, economical and socially?
You see nowadays, if we walking in with the market, so we can see a lot of stuff coming from the nanomaterial itself. Especially the cosmetics, like I think there is a lot of product is available right there. Now people are also using some smart dresses they are making with the fabrics, using this, smart polymers actually. So that's how they are trying to make it. But the idea, if we have to see, we need to be also, be careful in terms of like the toxicological effect, because once we employ there, we need to also see whether it is leaching, and then again, like one of the aspect of the research what we try to do to clean the water. So if we try to employ there, obviously if leached out, and the toxicological test itself shows some harmness to your to body, that is very big challenges. And also end of the day, it also affect to the environment. And the biggest challenge is what we are trying to face with the polymers itself. If you see, like there is a lot of debates is going around, and we can see actually like how to come up. And now this pandemic things with the COVID, you can see like a lot of polymers is being used actually, the plastic they're using by the mask and the protective way actually. So that is way, but we are also trying to be more eco-friendly in terms of looking the aspect actually, like how we can try to be more eco-friendly and public safety way by utilization of certain kind of this nanomaterials.
Oh, sir. So next question is, what type of linkage will develop between silicate and nylon in hybrid materials?
I have not seen that one we have not done with the nylon actually, but obviously like it goes with in terms of the preparation, because if you want to make the silicon carbide, then you need to also look actually like what you want to prepare, what you want to make the final resulting material, which is going to be alpha silicon carbide, beta silicon carbide, which is the most abundant form of the silicon carbide itself. So depends like what you are looking for.
Okay, sir. So next question is, how to make small silica nanoparticle with large pores?
I think I did cover there, and I think I wanted to avoid this question, but it's fine. That is why I did try to cover, like when we were trying to show the whole sol-gel process, because during that sol-gel process, you can try to see like how you can create a gel or how you can create the powder. So those powder form, if you have to do the calcination, once you make your material, like your precursor material, and then you have gone through the sol-gel process, and after the sol-gel process, then you have to dry it, then you calcine the whole material. And once you calcine, then you need to look actually what are the sizes you can. We try to go like around close to 4 to 50 nanometer sizes actually. That is the way we try to prepare, and even after the calcination we try to do. But obviously, like if you are looking for the larger scale, that is the way actually, like you need to also plan actually how we have to go more further on that side.
Okay, sir. And how we can improve the errors in hybrid materials?
Sorry, I didn't get you this question.
How we can improve the errors in hybrid materials?
What is Arabs?
Errors, sir.
I didn't understand that one.
How we can improve the errors in hybrid
Oh,
materials?
errors. Oh, sorry. Okay,
Yes,
no, I get it.
Hmm.
You see, when I was trying to say, and even to highlight a little bit there, I try to like in our whole group. This is not only my research. This is the whole research group involved, where you can try to see like once you are using the pure polymer itself, and I show you the example of polycarbonates. There you can see like it's a very nice structure, homogeneous, and the size is uniform, so that's how you can see. But if when you take the waste source, which is like coal tar pitch, or whether you took the lignin or the craft lignin, you have seen actually a lot of problems we have generated. So to remove those kind of obstacle, we are still working on it actually, like how we have to go purify. Then obviously like in terms of like the purification, you need to see with the HF treatment, what I have seen the impurity, I have seen, so you there right there. So once you do the HF treatment, obviously you can remove the unreacted silica from there, and even the silica which is present in the silicon carbide itself. So, that is the one way to go. But obviously, like your target is also there in terms of how you can improve the yield, because you are looking for, if you're looking for the catalyst for the bigger production, then obviously you need more amount. So that is the one actually we are looking around at this moment.
Okay, thank you, sir. That's all from my side, sir, and thank you very much, sir, for giving time for questions and answer sessions. Now
welcome.
over to you, Rashi ma'am.
Thank you, OP sir. And thank you, Ajay sir, for explaining all these questions so elaborately. Thank you once again. Now, I would like to request Dr. Sanjeev Sharma, HOD Mechanical Engineering Department, to kindly give the vote of thanks. Sanjeev sir.
Yeah. First of all, I would like to very thankful to Ajay sir on behalf of Mechanical Engineering Department of Mechanical Engineering. I would like to very thankful to you, sir, for your informative and the knowledgeable talk. You are very well defined about the 21st century material system. In this, you have to talk about how the organic and inorganic material we can develop. In this, actually, you are also talking about the hybrid material, composite material, nanostructured material, and the material alloys. However, you are also talking about the packaging material, and this particular mechanical material is a very good example of polymer as well as SiO2. Means this is the organic material, inorganic material. You are also talking about the technique we have to use in industrial application, because of these are having very good properties, like it is having a hardness property, good oxidation property, heat resistance property. All these combined together, and it will give a very good wonderful material system. So I am very thankful to you, sir, that you are delivering this particular talk. First of all, I have to extend my thanks to Honorable Founder President, sir, Dr. Ashok K. Chauhan, sir, and the Chancellor, sir, Asim Chauhan, sir. He provided regular platforms to perform it, as well as I am very thankful to sir, our VC, sir, Professor P.V. Sharma, sir, the Pro Vice Chairman, ma'am, they will provide us approval for that one. And we are very thankful to our team and team leader, Professor Dr. Caesar, sir. He will give us a very good platform and to deliver this particular. And I am also thankful to our all department members like Om Prakash sir and Rasi madam. She will coordinate very good. So in this way, in this way, I am very thankful to you, sir. Thank you very much, you all.
Thank you, Dr. Ajay Mishra, sir, and thank you the entire team. Thank you all. Thank you so much. Bye.
Thank you so much. I really appreciate all your support and all the kind words. Thank you so much.
Thank you, sir. Thank you. Namaste.